Hey Wheat North, Mr. Yergler here. We're going to talk about gram stoichiometry. We've talked about mole stoich, but gram stoich is important because usually when you do stuff in the lab, you're calculating how many grams, you're measuring out grams because you have a balance. We can't directly measure moles, we always have to convert to moles. And so you need to be able to predict how many grams of one substance you're going to make from how many grams you have of your certain reactant, for example. Okay, so let's get started. All right, let's just do a little quick review on this. If you have a reaction and you balance it, these numbers, these coefficients tell you how many moles of each substance you have. So 2 moles of aluminum hydroxide is going to produce 1 mole of aluminum oxide and 3 moles of water. The same would be true if you're talking about individual molecules, right? 2 molecules of aluminum hydroxide would break apart to make 1 molecule of this and 3 molecules of water. And this is easy when we're dealing with whole numbers. When you react 2 moles, you get 1 and 3, right? But if you react 6.5 moles, this is where you would have to actually do stoich because it's not going to come out even. Your given would be the 6.5 moles over your goal, which would be also moles, but moles of a different substance. In this case, it's asking about water, and so you would put X moles of water here, and then using your balanced reaction, you would do something like 2 moles of aluminum hydroxide to 3 moles of water is the ratio between those two. Okay, and you use that ratio to figure out what X is. All right, we're going to do the same exact thing, except we're going to have to convert to grams first. Okay, so let's look at this example. Go ahead and pause the video and write down these homework tips. These are going to be really handy whenever you feel like you get stuck and you're like, I don't know what to do. This is your step-by-step procedure for how to do that. Okay. All right, so here's our notes. And you already have all this stuff for you. So here's our balanced mole equation. So this tells us how many moles of one substance, of each substance produces how many moles of the products, right? So this balanced mole reaction, that's going to be directly from the balanced equation. So we can just go ahead and fill these in. 2, 3, 2, and 2. Okay. So this is our balanced mole reaction. Let's also calculate, we're going to need to calculate molar masses. So we're going to do this from using the periodic table. So H2S, that's 2 hydrogens, they're each 1 gram. Sulfur is a mass of 32, so that'd be a total of 34. And make sure you write grams per mole here. The unit on molar mass is always grams per mole. We don't always do that in the mole sentence, but we really should because it's the number of grams in each mole. Oxygen, there's 2 oxygens, they're each 16, so that's a total mass of 32 grams per mole. Sulfur dioxide has a mass of 64. It's 2 oxygens, that's 32, and then another 32 for sulfur would be 64 grams per mole. And water's molar mass is 18 grams per mole. And again, those are all taken from the periodic table, just adding up the number of atoms. All right, now, think about this. Hydrogen sulfide is 34 grams per mole. So if we have 2 moles, because this is our balanced mole reaction, our balanced gram reaction is just going to be the multiplication between those 2 numbers. So that's going to be 68 grams. So 68 grams of hydrogen sulfide is going to react with 96 grams of oxygen. I'm just taking 32 times 3 to produce, what would this be, 128 grams of sulfur dioxide and 36 grams of water, right? So this is the same thing. We've just converted all of our moles to grams. And so just like you could say that 2 moles of this with 2 moles of that makes, these, you could also say 68 grams of this plus 96 grams of oxygen makes, this much of this stuff. And if we were to add the masses on both sides, it would be the same because of law of conservation of mass. All right, so now we're ready to look back at our question. All right, look at our given. We have 10.5 grams of hydrogen sulfide. Let's actually circle the stuff that we're going to be dealing with. We're actually going to be doing it in grams, so let's circle that, right? How many grams of O2? So we're going to also be dealing with this one. But again, this is in grams, and so we're going to need to use this number. Okay. So let's start with our given over goal, as always. Our given is 10.5 grams, and our goal is X grams of oxygen, O2. Now, we need a proportional relationship I should also have H2S here. We need a proportional relationship between H2S and O2. That comes from our balanced reaction. 68 grams of H2S is proportional to 96 grams of oxygen. Okay, so let's plug those numbers in. 68 grams of H2S over 96 grams of oxygen. Now, this side of the proportion, you might want to make a note of this. This side of the proportion is always going to come from the balanced reaction, and this is always going to be your given over your goal. Okay. Now, in the last unit, we were taking these numbers from the mole sentence. Now, in this case, we need the same proportional relationship, but now we're getting it from the balanced reaction. Okay, because the balanced reaction is telling us, what is the relationship between oxygen and hydrogen sulfide? Well, it's 96 to 68. Okay, let's go ahead and do cross multiply and divide, and you end up getting X equals 14.8 grams. Make sure you do the math and with a calculator and get the same answer as I did, and that would be O2. So 14.8 grams would be our would be the amount required to make sure you react all of that 10.5 grams. Okay. Let's flip it over to the back. Here we have another example, and it looks the exact same. In fact, I can actually show you on my slide. I have it ready. Here it is. We have a different equation and a different given, right, and a different goal, obviously. So let's go ahead and take a look at this. You should have 99.2 here. On yours, it should be fine. The one that I printed had the wrong number here, so I changed that. So we're going to start with 9.2 grams. The balanced mole reaction, let's go ahead and fill those in. Let's pause before we go any further. It's asking us to find the grams of silver carbonate. So that's going to be this one. And we're given iron iodide, iron 3 iodide, that's this one. So really, we're only going to use our final proportion down here is going to be the relationship between this number and this number. We actually don't really need to find these two. So let's save ourselves the time and just leave those blank. Let's go ahead and find our molar masses though for these two. Iron 3 iodide has a molar mass of 437 grams per mole. You really should be, I want you to be calculating these. Look on your periodic table and actually calculate these just to double check that you are doing it correctly. Okay? And if you're off by, if you're off by 1, if you get 436, that's just a rounding mistake. You and I are probably rounding differently. That's not a big deal. Silver carbonate has a molar mass of 276 grams per mole. Another good way to check yourself on these is often you can just Google silver carbonate and it will tell you the molar mass. Wikipedia usually has the molar masses, which is a good way to kind of quickly verify that you're doing it correctly. All right, so now we're just going to multiply these two, 437 grams per mole. And if we have 2 moles, then that's going to be double the amount. That's going to be 874 grams. And 276, 3 moles of that would be 3 times that number, which is 828 grams. Not a lot of room to write. All right, now let's take a look back at our question. 9.2 grams of FeI3 is what we're given, and we're going to do given over goal again. X grams of silver carbonate. So 9.2 grams of iron iodide is going to be equal to X grams of silver carbonate. Now we just need to figure out what X is, but we need a relationship that is known, right? The known relationship is between these two here. Make sure you have the same substance on the top and bottom. So if iron iodide is here, then we need to make sure we have iron iodide's number here on top. Fe. Take the time to write out the formula because it helps keep track of what you're doing. It kind of minimizes mistakes. I'm taking the time to do it. Obviously, I've done this 1,000 times. I wouldn't really need to do it, but I'm doing it because I'm showing you that it's helpful to kind of see that you're doing it correctly. All right, when you solve for X here, X turns out to be 2.4 grams, and our unit is grams of silver carbonate. Okay, and you could write that right there. If we have 9.2 grams of iron iodide, that's going to also, if we produce that much, we're also producing 2.4 grams of silver carbonate. All right. Now let's take a look at percent yield real quick. So I produced 9.2 grams of iron iodide. I should have also produced 2.4 grams of silver carbonate. Now, let's say you carry this out in the lab and you actually produce 2.6 grams of silver carbonate. We also want to be able to calculate percent yield, which is basically how close did you get to your theoretical value. Your theoretical value is what you calculated, right? What you theoretically should be getting if you were to actually do it in lab. But in lab, there's always a lot of variation, a lot of sources of error. So let's say you get 2.6 grams. Your percent yield is always going to be what you actually got over what you should have gotten, right? It's kind of like calculating a grade on a test or something like that. So we actually got 2.6 grams. We should have gotten theoretically 2.4 grams according to our calculations. And so that's 108%, which is acceptable. I mean, that's common for you to get over 100%. That's okay. I mean, it obviously means that there's more mass in there somewhere that you didn't completely get out. You didn't completely isolate your product, or you added, you have excess reactant, which we'll talk about that soon on what that is. But your substance is essentially contaminated in some way. There's something in there that's adding mass that shouldn't be there, and that substance that's adding mass is not silver carbonate, because if you added the right amount of reactant, then there's no way to make more than 2.4 grams, assuming you added the perfect amount of reactant, that is, which is often difficult. Okay. Now, this is just two examples of gram stoich. There's going to be plenty of practice in class for us to get more practice with it. It may seem confusing now, but make sure you come to class with any questions or confusions that you have so that you can get those cleared up when we practice it in class. All right, this is Mr. Yergler signing off.